Hello, am I audible? My name is Rahna. I am a postdoc from CEFCA, which is located in Teruel. I am working with Mohammed and Carlinos. Mohammed was a postdoc here before with the Nacho. So today I will be talking about the H-alpha emission line map in J-PLUS DR3 galaxies. So this is our CEFCA Institute, which is located in Teruel, which is a small city which has around 30,000 people, which is located between three main cities, Zaragoza, Madrid, and Valencia. So before coming to Teruel, I was in Shanghai, which has 30 million people. Then I did my PhD before my first postdoc in Shanghai. I did my PhD from India, basically from Bengaluru. And I am from South India. It's called Kerala. It's called Western country with a lot of nature places. So let me introduce our group at CEFCA. So this is our team, which include two researchers. Mohammed is the PI of this project, and Carlos is the research director in the astrophysics department. And me and Raul are the two postdocs in our group. Raul also did his PhD from here. And Sepida is a PhD student in our group. So these are the main objective of our research group. We call it J-IFU. Basically, we do the IFU kind of science with the J-PLUS and J-PLUS survey, which I will be explaining in next few slides. So we study the spatially resolved structure of galaxies. So my main work is basically on the spatially resolved star formation main sequence. So yeah, for the people who are not familiar with the J-PAS or J-PLUS surveys, this is our observatory of Astrofísico de Javalambre, which is located in the Javalambre mountain in Teruel, which is around 1.5 hours of drive from Teruel. So basically, we have two telescopes. One is 0.8 meter telescope, which has field of view of 2 degrees. And another one is T250 Javalambre survey telescope, which is 2.5 meter telescope. And the field of view is 3 degrees square. So these two telescopes are mainly for the survey-based telescope. We are planning to observe the southern sky in 8,500 degrees square. So these are the map of the 8,500 degree square of the J-PLUS surveys. So these blue are the first seed observation, and yellow is the first tier observation, and red is the second tier observations. So this is J-PLUS. J-PLUS has like more than STS's 5 filters. J-PLUS has 7 additional narrowband and medium band filters, which cover main emission lines like O2 and H-alpha and other absorption lines. The first data release of J-PLUS was in 2017. And the latest one is in 2022, which covered 3,000 degrees square of southern sky. Yeah. So, and J-PAS, which has 57 filters, 54 narrowband filters, 2 medium band filters, and 1 broadband filters. And it has the resolution of 0.225, but J-PLUS has 0.5 arcsecond per pixel. And the first data release of J-PAS was the mini J-PAS, which covered 1 degree square of 4 AGs field. And the latest one is there was new data release, internal data release, which released on 2023 October, which cover around it scanned 30 degree square field, and for all filters, which has covered 6.8 degrees square. Yeah. So basically, because of the large wavelength coverage and the contiguous narrowband, J-PLUS and J-PAS survey can be treated as low spectral resolution IFUs. So which will cover around 1/5 of the sky. So you will get a steady information of every pixel of the sky. But compared to the other IFUs like MANGA, MUSE, and CALIFA or other SAMI or other IFUs, the main advantage of JPAS and J-PLUS survey is its field of view. As you see from here, so this is the field of view of J-PLUS, which is 2 degrees square area. And as you see, the field of view of MUSE, CALIFA, and MANGA, which is very small compared to the full field of view of J-PLUS. This is actually 10 arc second to 10 arc second box. So the main advantage, the main uniqueness of J surveys, of course, it's large field of view. So we can get the complete structure of the galaxies, also study the environment of galaxies. Yeah, so my work is mainly on the spatially resolved studies in nearby galaxy. Most of the other researchers in CEFCA working on with the catalog. So we are the team, JIFU group is working on the resolved properties of galaxies. So my project, we divided into 4 different publications. So the first one is the emission line map of nearby galaxy, where we mainly focused on H-alpha emission line map. That is the subject of today's talk. And the second paper, we are focusing on the spatially resolved star formation main sequence. And the third one is the comparison of UV and H-alpha morphology of nearby galaxies using UVIT and galaxy surveys. I will explain the UVIT surveys in next few slides. And the last one is spatially resolved star formation in early type galaxies. So these are like different projects already we submitted in JPLUS website. So here, so for the first project, we are focused on H-alpha emission line map for the initial analysis. So we mainly have the galaxies with the redshift range of 0.0 to 0.17 redshift. So first we cross-matched with the J-PLUS with other IFU to validate our method of building the emission line map. So we used CALIFA, MANGA, and MUSE, thanks MUSE. For MANGA, we have 123 galaxies cross-matched with the J-PLUS DR3. And for CALIFA, we are 100 galaxy, which is cross-matched with the J-PLUS DR3. And from FANGS, there are 2 galaxies which has observation in J-PLUS. So the final outcome of this project will be the cross-matched catalog of this J-PLUS DR3 with the MANGA, CALIFA, and MUSE. And we also give the emission line map of thousands of galaxies in total DR3 catalog. So this is the flowchart of our pipeline, JIFU pipeline. So basically in the pipeline, we have to like, it is giving the J-PLUS all the field of information of J-PLUS and 0-point magnitude. And based on the coordinate information we are giving, like we just have to give the catalog information and it will finally build the H-alpha emission line map. So first step was the PS of homogenization. After downloading the images from J-PLUS, it will do the PS of homogenization. It will, based on the worst PSF in all filters, it will homogenize all the PSF in all the images. Then we follow the 3 filter method for creating emission line map. So for that, 2 filters. For example, H-alpha emission line map, we use ISTSS and RSTSS filter to trace the continuum, and the J0660 filter to trace the H-alpha emission line. So yeah, here you see these 2 are the STSS filters, RSTSS and ISTSS, and this is the J0660 filter which cover the H-alpha emission line. And we mainly use GNU Astro, developed from Muhammad. Basically, this is the GNU astronomical utilities to study, like analyze the astronomical data. So most of the analysis we are using GNU Astro routine. Yeah. So for validating our method, we are also building the emission line map from other IFUs like MANGA, MUSE, and CALIFA. For this, we follow 2 methods. One is 2D method, one is 3D method. In 2D method, we basically build the pseudo narrowband first. ISTSs, RSTSs, and J0660 filter. Then we follow the same 3-filter method as we followed from the JPLUS to build the emission line map. And for the second 3D method, we first subtract the continuum from the cube itself. We follow the GNU Astro sigma clipping method. Then we convolve the continuous subtracted cube. We convolve with the J0660 filter. And finally, we build the emission line map. So for MANGA and MUSE, which has the full coverage of ISTSs, RSTSs, and J0660 filter. But CALIFA, the problem is it is not covering completely the I band. So we are building in the paper, we are only producing the emission line map based on the method 2. Yep. So let me show you some emission line maps from MANGA and JPLUS. So for MANGA, the wavelength coverage is almost similar to JPLUS, and the spatial resolution is also similar, 0.5 arcsecond per pixel. And the field of view, of course, JPLUS has more field of view, 1.4 into 1.4 degrees. So these are the output from our pipeline. So this is the emission line map from JPLUS based on 3-filter method. And this is from MANGA, again 3-filter method by building the pseudo narrowband. And this is from 3D. So this is the radial profile, and we are getting almost like same result from 3 different methods. So for creating this map, for building the radial profile, we have convolved in the same pixel scale of MANGA and JPLUS, and also the field of view we cut based on the MANGA field of view. And actually, what we are seeing in MANGA is only the central part of this galaxy. But this is the emission line map from the JPLUS. You will get the complete picture of this galaxy with the JPLUS. This is the SGSS image and JPLUS emission line map. And this is another example. Again, 3 different methods, JPLUS 2D method and MANGA 2D method and 3D method. And in next slide, you see what is the difference of field of view, how it matters. So for the MANGA cube, it's only one small star-forming region in this galaxy. But for the JPLUS, we are getting the full picture of this galaxy. So we are building the emission line map of the full galaxy, complete galaxy. And next to the CALIFA, moving to the CALIFA, CALIFA has the wavelength coverage from 370 to 700 nanometer, which is not covering some part of the red part of the spectrum. And the resolution is poorer than the JPLUS. It has 1 arcsecond per pixel. And the field of view is 1 arc minute. We are using the latest version of the CALIFA cubes, where they have improved the resolution. And here are the examples. Again, we didn't show the 2D method because it is not covering the ISTSS filter. So this is the radial profile and the emission line map of CALIFA. Again, the CALIFA cube, JPLUS is convolved, the pixel scale is scaled into the same pixel scale of CALIFA. And here you see the complete H-alpha emission line map of this galaxy in JPLUS. And this is the field of view of CALIFA. Yep, this is another example of the same CALIFA galaxy, which has this one is a JPLUS 2D image, H-alpha image from 2D method, and H-alpha image from 3D method. And moving to the MUSE data, so we have 2 galaxies. One is NGC 1087, and this one, which cover 6 field. Like it's actually 6 field of MUSE combined to get the complete structure of this galaxy. And another one is NGC 628. This one. This has actually 12 field to cover the central part of galaxy, not completely covering the full galaxy. And this is the wavelength range, and the spatial resolution is far better than JPLUS, but the field of view is very small, 1 arc minute. And here are the images of NGC 1087 in R, SGSS, and AJ0660 filter before continuous subtraction. Here you see the emission line map, H-alpha emission line map after continuous subtraction. So this is the J-PLUS emission line map. And this is the MUSE 2D, using 2D method, and H-alpha from the 3D method. And this is the radial profile. And it also matches very well with within 3 methods. Again, this is also the MUSE cubes are the scaled into the same pixel scale of J-PLUS here. Here the second galaxy NGC628, which is, this is a J-PLUS image, and this is MUSE image. As you see, the MUSE could not cover the full field of view of this galaxy within, like, even though with the 12 fields. So here you see the H-alpha emission line map. But for this galaxy in the MUSE cube, it doesn't have the sky part. So it is basically the over subtracted the sky. That's why there is a little difference in the flex in the MUSE cube, MUSE flexes compared to the J-PLUS. Yep, this is the complete structure of this galaxy of the H-alpha map of NGC628. And here are some other examples. We found some of the galaxies still there is some residue from the star. We are looking into more details of each galaxies. And there is another example, again, RSTSS and the H-alpha map of M101. And the other one, this is my favorite one, M33. You can see the H-alpha, even the bubbles in the galaxy. This is the RSTSS and the H-alpha map of M33. Then after the H-alpha emission line map, we also provide the photospectra of clumps in galaxies. This is an example. So this is the H-alpha map of NGC 1087 in J-PLUS. We basically use GNU Astro routines for the object detection and the segmentation. And these are the clump segmentation map of this galaxy using GNU Astro. And here, then we, based on the size of these each clumps, we get the photospectra, we get the flex from each filter image of J-PLUS, and also from MUSE for the comparison. And these are the labels of these clumps. And as you see, this is this photospectrum of each clump. There are 4 clumps. And here you see the blue one is from MUSE spectra, and the orange one is from J-PLUS photospectra. And yeah, these are the 4 different spectra. And you can see the emission line in H-alpha. And here you also see the O2 lines. The emission in O2 is very prominent in this spectra. Yeah, so we just in the first as a preliminary check, we just labeled the photospectra, the clumps showing the O2 emission clearly as a magenta color. So we there is a pattern of most of the outer clumps has showing the O2 compared to the H-alpha, maybe because of the extinction. Then for the another galaxy, CALIFA, also we did the same analysis. This is again H-alpha map from J-PLUS, and using GNU Astro, this is a segmentation map from the H-alpha image. And so for each clump, we have taken the photospectra from J-PLUS for all 12 filters, and also from the CALIFA spectra, like the CALIFA cube, we took the spectra for each clump. And here are our results. Here you see the comparison of the CALIFA and J-PLUS photospectra of each clump. So after this work, so basically we are providing in the first paper, we will be releasing the H-alpha map of these 200 galaxies, and we validate our method for comparing with the other IFUs. And also we provide the catalog of photospectra of all the clumps in all these 200 galaxies. Then after that, we are planning to apply the same method to all the galaxies in J-PLUS DR3 within the redshift of 0.017. And then we study the spatially resolved star formation main sequence. So basically, the main sequence of galaxies, the correlation between the star formation rate and stellar mass. So in global way, it is like integrated property. It is derived from integrated property. So for our study, we basically do the spatially resolved properties of this strong relationship, like star formation and stellar mass. Yeah, so that is our plan. We are studying the spatially resolved star formation main sequence of galaxies. This kind of studies are already done with the CALIFA, but the CALIFA is limited with the field of view of, because it cannot cover the full galaxy, and also limited number of target. So we are focusing on more galaxies with the full field of galaxies. So with this project, we are planning to provide the full emission line map of all the galaxies, also the star forming clumps, and the Rayleigh distribution of star formation. And also finally, we build the relation of the spatially resolved star formation main sequence. Then moving to the third project. So basically, after building the emission line map of all the galaxies in H-alpha, we are planning to compare with the UV, ultraviolet. Here is an example. As you see, this is J0660 filter before continuous subtraction. This is H-alpha map, and this is the UV. So this is from UVIT mission. So we already have studied this galaxy in UVIT, basically to study the extended outer disk, the star formation in the extended outer disk. So basically, we are comparing the two different stages of star formation. So H-alpha can trace the early O and B type star, more massive star, but UV can trace more hot and less massive O and B type star up to 100 million years. So similarly, like we are planning to study the full sample of our J-PLUS DR3 galaxy and compare based on the availability of UVIT data. We compare with the H-alpha, and UVIT has 0.41 arcsecond per pixel resolution, which so even J-PLUS has 0.55, so we can do the pixel to pixel comparison for the star formation. Yeah, here is the HR. This is actually H1 disk of this same galaxy, as you see. This kind of XUV galaxy, which shows the extended UV emission beyond the optical radii. And it also shows the H1 observation as same as the star formation in UV. So we will be using UVIT data, also GALAX, for the UV observation. So right now, there are 317 fields are observed with the J-PLUS. One field is 28 arc minute. So we will be like cross matching with the UVIT with the J-PLUS. And we build we already have the pipeline to build the H-alpha maps, and we compare the UV and H-alpha, how the star formation is distributed in UV and H-alpha. And also we are planning to study, find the XUV type of galaxies within the J-PLUS and UVIT, like comparing how the star formation, how the disk is evolved in UV compared to the H-alpha. The last project is on, sorry, what is the time? Oh, sorry. Okay. So the last project is on spatially resolved star formation in early type galaxy using J-PLUS. So where we mainly focused on early type galaxy like lenticular and elliptical galaxy, which shows star formation. Here is an example. So this is actually elliptical galaxy in J-PLUS and J-PLUS RSTSS filter and J0660 filter. So as you see in this, if you check in the UV, you can see some star formation in this galaxy. And also in H-alpha, this is a H-alpha map of from J-PLUS. So we are studying this kind of galaxy, which is lenticular or early type galaxy. But when you check H-alpha or a UV, you will see the star formation. So we are planning to study the environment of this galaxy, how the star formation is occurring in this galaxy using the J-PLUS and also with the UVIT. We are basically using the UVIT and J-PLUS data for this study. So all these 4 studies are connected each other. First we are building the H-alpha map. Then from the H-alpha map, we are studying the star formation main sequence. Then we are comparing with the UV. And finally, some sample of early type galaxy we are using and studying the star formation in these galaxies. So I also want to introduce my previous research. So before coming to CEFCA, I was in Shanghai and my PhD was from India. So for my PhD, I mostly involved in UVIT mission, which is UVIT is actually, the AstroSat is actually launched in 2015. And which has 5 instruments. Like these are the 5 instruments. This works in X-ray and UV and optical. And the UVIT is one of the instruments. It has 237.5 centimeter telescope and the field of view is 28 arc-minute. And the time resolution is 0.035 seconds. And the pixel scale, as I said, 0.41. And the spatial resolution is 1 arc-second. As you see these 2 galaxies, this is from the same galaxy in UVIT and Galax. So the spatial resolution is 4 times better than the Galax. So my work was mainly on the pipeline development after launch of AstroSat. And then I also have a paper on the UVIT in-flight performance where we study the performance of the detector, FUV and NUV detector. And also my thesis was mainly on the star formation on in galaxies with the UV, FUV and NUV data. And also I have involved in some like project on outskirt of XUV galaxies where we mainly focused on the star formation in the outer disk of galaxies. And in China, I started my JPLUS journey from China. So first I was involved with this was the high redshift group in Shanghai Astronomical Observatory, which is located in Shanghai, the middle of the city. So we studied mainly the Lyman Alpha Nebula around high redshift QSOs, which trace mainly the neutral hydrogen in circumgalactic medium. Then after that, I moved to CEFCA, where my study is mainly on J-PLUS. So I have experience with the J-PLUS and J-PLUS. I also have another project with the J-PLUS on changing loop quasars. Yeah, so I already explained what is AstroSat. These are the filters of AstroSat. These are the FUV filters, 5 FUV filters. And UVIT has 5 NUV filters and also 5 WIS filters. Basically, WIS filters are used for tracking, not for the scientific purpose. And NUV, like the NUV detector is already stopped in 2018. So after 2018, you will be only available the FUV data. So this is the pointing, UVIT pointing in the sky. And if you want the reduced data, you have to go to AstroBrowse website and you have to create a account there and you have to search your own galaxies and you will get raw data as well as the reduced data from this website. So each point is actually 28 arc-minute field of view. So currently I'm also working on this outer disk star formation, basically, which shows the star formation beyond the optical radii, beyond the classical star formation threshold. And so the initial studies was done in Telkar et al. 2005 on M83 and NGC 4625. That was using Galax. They found the extended UV emission compared to the optical disk beyond the optical radii. And they also found that they have done a systematic search for this kind of galaxies in 2007 by Tilker et al. They have used 189 galaxies, and they found 29 of this galaxy exhibit XUV emission. And they classified this type of galaxy in type 1, type 2, and type 3 based on the structures, how it is distributed. So in type 1, basically it shows the UV structured UV emission. Yeah, beyond the optical radius to 27, the FUV threshold value of 27.25 magnitude per arcsecond square. So basically, this kind of galaxy which shows the structured UV emission, this type of galaxy is called a type 1. And type 2, which is actually, it has the high extended blue disk. So the red contour is actually the contour enclosing 80% of K-band. And if it has the large extended UV disk, which is this kind of galaxy, they classified as type 2. And mixed type has both type 1 and type 2 features. So these are the few galaxies which shows the extended UV emission observed in UVIT with UVIP. Yeah, so this is the summary of my talk. I finished within, I think, 35 minutes. I don't know, I was very fast or not. Anyway, so the main summary of my work is the wide field of view and spatial resolution, wavelength coverage, and contiguous narrowband filters act like a low resolution IFU for J surveys. It is suitable for spatially resolved studies. And we are providing the emission line map of the thousands of galaxies with our first paper. And also we are providing the ACDs, like you can have the ACDs of each star-forming clumps and study their properties. One is like, for example, the spatially resolved star formation. You can have the spatially resolved information of star formation and the stellar mass. And you can build the relation between these two, the star formation main sequence. And so, but JPLUS is more like, it has more filters, 54 narrowband filters. So it has more resolution, spectral resolution than JPLUS. And it also covers most of the prominent emission lines. So we are expecting to have public data release in this year. So already internal data release is, the first data release of JPLUS is out in 2023 also. The mini JPLUS and JNEP observation also already available in public. And after this work, we are expecting to have our next 3 papers on star formation main sequence and the comparison of H alpha and UV and star formation in early type galaxies. Yep. Thank you. Questions?
Thanks. Very nice talk. I'm interested particularly in the star formation in early type galaxies. So is there any selection of the environment of your observations for the early type, or just everything that is local?
In our plan. So basically, we are taking all the early type galaxy and we compare the FUV and UV, UV and H alpha, and first we select like based on the, it's not about the environment, like we select all the samples and based on the morphology. Because in that as you see here, if you check before continuous subtraction, if you see only in JPLUS filters, you are not able to see the structures, right? So only in the H alpha map, after continuous subtraction, only you are seeing some features. And also look into FUV and UV. So if we are not looking into the UV part or H alpha, we are not able to identify whether it has star formation or not. So yeah, so the selection is basically based on the like structures. And also then we have to classify whether the environment, how the environment is depending, whether it has cluster environment or these are the individual galaxies. Yeah, no interaction. Should I explain anything? If you're not understanding, I can explain. Yeah, sure. Thank you again.